High-voltage transformers are among the most important machines in the modern world, quietly powering entire cities, factories, hospitals, and data centers by stepping electrical energy up or down with astonishing precision. Without them, long-distance transmission would be impossible and the global grid would collapse. Yet few people ever witness the enormous industrial process required to build one. A process involving precision-engineered steel cores, miles of copper windings, oil-filled tanks the size of shipping containers, drying ovens, vacuum insulation systems, and high-voltage test bays powerful enough to simulate lightning strikes. And today on the How Factory, we're going inside the factories, where these massive transformers are designed, wound, insulated, assembled, vacuum-dried, oil-filled, tested, and prepared for decades of continuous service. What looks like a silent steel box sitting behind a substation fence is actually one of the most carefully engineered machines ever created. Every transformer begins with the core, the magnetic heart of the system. Factories start by cutting thin sheets of grain-oriented electrical steel, a special alloy designed to guide magnetic flux with minimal energy loss. These sheets are coated with insulating varnish and cut into precise shapes by CNC punch presses. Automated stacking machines build the core layer by layer, with each lamination slightly offset to reduce noise and eddy currents. The core may weigh tens of thousands of pounds and stand several meters tall, yet its tolerances must be exact. Even minor variations in alignment can increase losses in heating inside the transformer, so lasers, measurement bridges, and robotic arms monitor the stacking process. When finished, the steel core is bound tightly by clamps and frames to maintain rigidity during operation. With the core complete, the next stage begins: manufacturing the windings. High-voltage transformers typically contain both primary and secondary windings. Massive coils of copper or aluminum conductor wound around formers or directly around core legs. The conductor arrives as large spools of enamel-insulated wire, foil, or rectangular bars. Winding machines, enormous rotating platforms, pull the conductor under constant tension as it forms layer after layer of turns. Each turn must lie perfectly flat because any misalignment can lead to hot spots or insulation breakdown under high voltage. Between layers, operators insert insulating sheets of craft paper, pressboard, or advanced polymer materials. The insulation must hold back thousands or even hundreds of thousands of volts, so factories track every layer, turn count, and tension reading digitally. As voltages increase, windings become more complex. High-voltage coils may be built using helical winding, disc winding, or continuous transposed cable, a special conductor where strands are constantly woven to equalize current distribution and prevent overheating. Oil ducts and cooling channels are built into the windings for fluid circulation. Spacers and pressboard cylinders ensure mechanical stability. When windings experience short-circuit forces in real-world operation, they may face tons of mechanical pressure trying to crush or deform them. To withstand such stress, manufacturers bind windings using epoxy impregnation, compression rings, and fiber-reinforced insulation structures that hold everything rigid. Once the winding coils are complete, they undergo preliminary electrical tests. Technicians measure resistance, insulation strength, turn-to-turn integrity, and partial discharge levels. Any void, contamination, or misalignment can cause tiny electrical sparks, partial discharges, that slowly degrade insulation. Transformers are designed for 30 to 50 years of life, so catching flaws early is essential. Now it's time to assemble the active part, the core and coils combined. Using overhead cranes, teams lower each coil onto the core legs with extreme care, aligning everything within millimeters. Pressboard barriers, spacers, and insulation cylinders are added around the coils to form structural walls that maintain electrical clearance and direct the flow of cooling oil. Lead connections, thick copper conductors, are installed to link windings to bushings, tap changers, and external terminals. On-load tap changers, which allow operators to adjust voltage while the transformer is energized, are mounted either inside the tank or in a dedicated compartment. These tap changers use complex mechanical switching systems submerged in oil, requiring precision machining and assembly. But before the active part can be enclosed inside the steel tank, one of the most important stages must occur: drying. Moisture is the enemy of high-voltage insulation. Even a tiny amount of water can reduce breakdown strength dramatically and cause catastrophic failure. To eliminate moisture, the entire core and coil assembly is placed into a vacuum drying oven, a chamber the size of a shipping container. Inside, the transformer is heated under deep vacuum for many hours or even days. Heat drives moisture out of insulation materials, while the vacuum pulls vapor away. Sensors track every temperature zone, pressure level, and evaporation rate. When moisture levels drop to near zero, the assembly is ready for impregnation. Meanwhile, the transformer tank, the massive steel structure that houses everything, is fabricated in another part of the plant. Steel plates are welded into shape using automated welding systems and robotic arms. Weld seams undergo ultrasonic and X-ray inspection to ensure they are perfectly sealed, because the tank must withstand pressure fluctuations and hold thousands of liters of insulating oil. Once welded, the tank is blasted clean, coated with corrosion-resistant primers, and oven-cured. Radiator fins or oil coolers are welded to the outside to increase surface area, helping dissipate heat during operation. Some transformers use forced air cooling with fans. Others use oil pumps or heat exchangers to regulate temperature. Now comes one of the most dramatic steps in transformer manufacturing: oil filling under vacuum. After drying, the active part is lowered into the tank. The tank's lid is welded or bolted in place, leaving openings for bushings and accessories. The entire tank is then placed under vacuum for hours. This removes the last traces of air inside the windings and insulation. Under vacuum, insulating oil, specially refined mineral oil or synthetic ester, is pumped into the tank. The oil flows into every channel, void, and duct, displacing air and forming a dielectric barrier that improves voltage strength and prevents arcing. Oil may be filtered, degassed, and heated as it enters to ensure purity. Filling continues until the transformer is completely submerged and the vacuum is gradually released, so the oil saturates insulation under atmospheric pressure. Once filled, the transformer enters final assembly. Bushings, giant porcelain or composite insulators, are installed on top. These components guide high-voltage conductors safely into and out of the tank. Some bushings handle hundreds of kilovolts, so they contain internal capacitive layers designed to distribute voltage evenly. Technicians connect internal leads to each bushing using robust copper bars. Control cabinets, temperature gauges, pressure relays, oil level indicators, and cooling fan wiring are all mounted. Tap changers receive their final adjustments. Nitrogen-filled conservator tanks, small reservoirs that accommodate oil expansion, are installed with flexible bladders that keep oil isolated from air. Now the transformer moves to the test bay, a high-voltage arena that resembles a sci-fi laboratory. These rooms are shielded, acoustically insulated, and filled with towering test equipment capable of generating voltages far above operational levels. Before shipping, each transformer must pass a series of tests: applied voltage tests, induced voltage tests, turns ratio tests, partial discharge measurements, insulation resistance tests, impedance checks, and lightning impulse tests. During the lightning impulse test, massive Marx generators deliver a surge that simulates a lightning strike hitting the power grid. The transformer must withstand multiple pulses without breakdown. Sensors monitor current waveforms, discharge events, temperature, oil behavior, and insulation response. If the transformer passes, it's certified for decades of operation. Once testing is complete, the transformer is drained of some oil to prepare for shipping if required, sealed, painted, and mounted onto massive transport frames. Oversized load trucks or special rail cars carry the transformer to substations. At the installation site, technicians refill the oil, reassemble bushings, reconnect tap changers, and run final checks. When connected to the grid, the transformer becomes part of a vast electrical network, often running continuously for 40 years or more. Inside its steel walls, magnetic fields will cycle millions of times every second. Copper windings will carry staggering currents, and insulating oil will circulate silently. All because of the meticulous engineering and manufacturing that occurred inside the factory. What makes transformer construction so extraordinary is the fusion of heavy industry with microscopic precision. These machines weigh hundreds of thousands of pounds, yet their internal clearances are measured in millimeters. They handle voltages that can leap through air yet remain stable thanks to layers of carefully dried insulation. They endure enormous mechanical forces while maintaining perfect alignment. Every weld, every winding, every lamination, and every insulating sheet contributes to long-term safety and reliability. And that is exactly how high-voltage transformers are designed: wound, insulated, vacuum-dried, oil-filled, assembled, tested, and deployed. A stunning blend of mechanical engineering, material science, electrical design, and industrial craftsmanship powering the global grid. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products.